Welcome to the Ontario High School video podcast regarding balancing chemical equations and reaction types. And this is going to be a primer, meaning that we're going to deal with the very basics of this topic. We'll be talking about chemical equations, what the symbols mean. We'll be talking about how to translate word descriptions into chemical equations, balancing chemical equations, and then the major groups of chemical reactions, the major types. So that's what we're up for today. And one of the things that may be helpful when we're going to talk about word descriptions and changing that into chemical equations, it's imperative in order to be successful at this that you know how to write the correct chemical formulas. So there is a previous video podcast called Naming Inorganic Compounds that would be very helpful to you if that's an area of weakness for you. So you may want to go back and review that one as well, depending on how you do with this. When you look at a chemical equation, there are certain symbols that have meaning. For instance, the single arrow means reacts to, yields, or produces or forms. A double arrow is the same, but it indicates the reaction is reversible or at equilibrium, which is a topic we'll talk about in the future. The delta sign, which looks like a triangle, is often written above the arrow in the equation, and it represents that heat is added to a reaction. When you see an S in parentheses following a chemical formula, it indicates that it's a solid. An L in parentheses indicates that it is in a liquid phase. G in parentheses indicates that it's in a gas phase. AQ represents something that is dissolved in water. And sometimes when a reaction occurs that product is formed that has a gas, there will be an upward arrow there instead of just a G. So if you see that upward arrow, it means that it's a gaseous product. If it's a reaction in which a precipitate, which is a solid product that forms from when you mix two different solutions together, we'll talk about precipitation reactions more later, but you'll see a downward arrow rather than just an S, indicating that it's a result of the chemical reaction that has occurred. Here we want to translate a word description of a chemical reaction into a chemical equation. So we have 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to produce 2 moles of water vapor. The 2 with the hydrogen gas represents the coefficient, which we'll eventually look into as mole ratios in balanced equations, but for right now it's a coefficient of 2. Our hydrogen gas is H2, and hydrogen is one of those elements that is diatomic in its free element form, so it will never be written as H as a free element, it will always be H2. We have the G in parentheses representing the gaseous phase for the hydrogen, and it's being reacted with 1 mole of oxygen, so we put plus. The O2, oxygen is another one of those diatomic elements in its free element form. Oxygen will always be written as O2. The phase represented by the letter G in parentheses. The arrow represents that it's producing something, and the product is 2 moles of water vapor. So there should be a G in parentheses following the H2O to represent its phase as a gas. The foundation for why chemical equations are balanced is this. In chemical reactions that are non-nuclear, and chemical reactions are non-nuclear. If it's a nuclear reaction, we call it a nuclear reaction. So don't mix those up. In chemical reactions, the nucleus is not affected. What is affected is how the electrons are arranged, whether they are shared or whether electrons are transferred or acquired in a chemical reaction. And because of this, matter is neither created nor destroyed in non-nuclear chemical reactions. So the law of conservation of mass is what provides the foundation for balancing chemical equations. The mass of the chemical reactants that go into the reaction will be the same as the mass of the products formed from the reaction. Matter is rearranged in chemical reactions, it is not created or destroyed, and this is critical to remember. So, to further illustrate this, atoms in a chemical reaction rearrange. The number of reactant atoms must equal the number of product atoms of each element after the rearrangement. That is the key to balancing equations. If you start with 5 sodium atoms on the reactant side of the equation, you must account for those 5 on the product side of the equation. You can't have 6 and you can't have 4. You must have the exact number of each element's atoms on the product side that you have on the reactant side. Here are some basic hints that I have found helpful through the years in terms of approaching balancing equations systematically rather than haphazardly. So when I'm balancing by inspection, and there'll be a way of balancing that is not by inspection, that uses methodology that is associated with oxidation reduction chemistry, and I will teach that in a podcast down the road. But for right now, until you get to oxidation reduction, the chemical equations that we're going to deal with should be able to be balanced just by inspection. And here's the system that I use. I balance metals first. I then balance nonmetals next. I balance hydrogen second to the last after I balanced everything else except oxygen. And then I balance oxygens last. So if you approach chemical equations this way, I found that it generally will lead to success if you follow this order. Let's look at a sample problem. Here we have solid aluminum metal reacting with oxygen gas to form solid aluminum oxide. So in our first stages, we're going to balance the metal first, which is aluminum. I have 2 aluminums in the product side of the equation in the Al2O3. So I'm going to put a coefficient of 2 in front of the aluminum on the reactant side of the equation. Note that the only way I can balance equations is by changing coefficients or adding coefficients. I cannot change a chemical formula that is correctly written, and I cannot balance using subscripts. It has to be done by coefficients. So I have my 2Al plus O2 yields Al2O3. Now, when I do this, I now can go to my oxygen, and as I look at my oxygen, I have 2 oxygens on the left in the O2 and 3 oxygens on the right in the Al2O3. In order to fix that, when you have 3 on one side and 2 on the other, it's good to take them both to the least common multiple, which would be to 6. So I'm going to put a 3 in front of the O2 to get 6 oxygens on the reactant side, and a 2 in front of the Al2O3, which would give me 6 oxygens on the product side. Now, when I put that coefficient in front of the Al2O3, it then changes the number of aluminums that I have. I now have 4 aluminums on the right side, or the product side. I need to get 4 aluminums on the reactant side, so I'm going to change that coefficient of 2 to a coefficient of 4, so that I have 4 aluminums plus 3O2 will yield 2 Al2O3. So my balanced equation then is 4 aluminum plus 3O2 yields 2 Al2O3. Here are 3 equations that I'd like you to balance on your own and then come back and look at the solutions. So if you would write these chemical equations down, and the nice thing on your paper, you can write them all on one line. In order to fit them on this, I had to put the products on a separate line. But if you'll go ahead and write these all out on one line, pause the podcast, balance these, and then when you're ready, come back and I'll show you the solutions. Welcome back. Here's the solution to part A. Here we have aqueous sodium sulfate reacting with aqueous calcium chloride, and we form a precipitate here, and all a precipitate is a solid that forms when you mix 2 ionic solutions together. And then we also form aqueous sodium chloride. Now, here's a hint I want to give you. We have a polyatomic ion here, the sulfate ion, which is SO4 with a 2 negative charge. The sulfate ion stays the same on both sides, and you have to be really careful with this. When you look at a reaction like this, here we have the sulfate the same as on both sides. You have to make sure that the sulfur from the sulfate does not show up on the product side in some other form as well, because there are some reactions in the oxidation reduction realm where that will occur. because the sulfate is the same on both sides and sulfur doesn't appear in any other form, you can treat it as though you would have just a single atom in terms of balancing purposes. So I balance my metals first. I have 2 sodiums on the left, so I put a coefficient of 2 in front of the NaCl on the right. My calcium, I have 1 and 1, so I'm okay there. I have 1 sulfate on the left and 1 sulfate on the right, so I'm okay there. And then when I put my 2 NaCl on the right, there's 2 chlorines there. And there are 2 chlorines in the calcium chloride, so this equation is balanced. The solution to part B for the C8H18, which by the way is octane component in gasoline, plus O2 yielding CO2 and H2O. When you first go to balance this, you get 8 CO2s for the 8 carbons that are on the left, and then 9 H2Os for the 18 hydrogens that are on the left are balanced by putting a coefficient of 9. When you add the oxygens together, you get an odd number. Okay, so 8 times 2 is 16 oxygens in the CO2 plus 9 in the H2O make 25 oxygens. And you run into a dilemma here. You have an odd number of oxygens on the product side and an even number on the reactant side. These will not balance without using a decimal number. So I put in originally here C8H18 plus 12.5 O2 yields 8 CO2 and 9 H2O. Now, it is generally considered improper to have a decimal number coefficient or a fractional coefficient. So the way that we can get rid of that decimal is to multiply by the smallest whole number possible to take everything to a whole number, which would be 2. So we then have 2 C8H18 plus 25 O2 will yield 16 CO2 and 18 H2O. Finally, we have the solution to part C. Here we have H3PO4, which is phosphoric acid, being added to potassium hydroxide, and this forms a salt, potassium phosphate, and water. We'll talk about this type of reaction later on. When you add an acid, aqueous acid, to a metal hydroxide, which is a hydroxide base, you'll form a salt. Again, here is potassium phosphate and water. And these type of reactions are a reaction that we'll call neutralization reactions, part of a general classification of what we call double displacement reactions. But here, the phosphate ion is the same on both sides. We balance the metal first, so there are 3 on the product side, so I put a 3 in front of the KOH, and then again we have 1 phosphate on each side. We're okay there. So I then have to look at hydrogens. So I have 3 hydrogens in the phosphoric acid, 3 in the potassium hydroxide, which gives me 6. So I then put a 3 in front of the H2O to balance my 6 hydrogens. Then I count up my oxygens. I have 3 oxygens in the H2O on the product side. I have 4 in the phosphate ion. When I look up at my phosphoric acid, I have 4, and then 3 oxygens in the KOH. So at that point, I'm balanced. This is the end of part 1 of the video podcast series having to do with balancing chemical equations and reaction types here at Ontario High School. I want to leave you with a quote from Ayn Rand. "Do not ever say that the desire to do good by force is a good motive. Neither power lust nor stupidity are good motives." Stay tuned for part 2. I wish you well.